Hello. Today we're going to be talking about Chapter 7, or about sediment and sedimentary rocks. Now we know that sediment is a material that is deposited as an aggregate, which means it's just a loose association of different kinds of solids. Depending on where they came from, what the parent material was, will determine what kind of rocks they are, but they're compacted or cemented together, which we'll talk about what that actually means. And geologists use the texture and composition of these rocks once they're in rock form to determine what kind of sedimentary rocks they are. There are a variety of features preserved in the sedimentary rocks, which are good indicators of how the original sediment was deposited. So if it's sandstone versus small pebbles, you'll know that one came from a beach, possibly the other came from a stream bed. We'll talk about the sedimentary facies, which means face, obviously, or front, and it can be traced across geographic areas to determine how big a geological region was or the geological history of a region. We'll also talk about the evidence of prehistoric life and what that evidence supplies in the way of paleoecology, and which is basically the form the fossils took, and how they're found in the different sedimentary rocks. And most fossils are found in sedimentary rocks. Sedimentary rocks are also associated with petroleums and natural gas, uranium and iron, a bunch of these things that we use as natural resources or reserves. And we also know that high levels of uranium, which are found in a lot of these clay soils, result in radon outgassing, which then also can cause problems for people if they get cancer from the radon. So here we have a slide of how sedimentary rock forms. So the first thing that you see is water right here coming down as rain. And we call water the universal solvent. The reason we call it the universal solvent is it is the smallest polar molecule that exists in nature, and because of that polarity, it tends to dissolve salts. We know when we put salt in water, it dissolves pretty rapidly, and that's due to the polar activity of this molecule. It also dissolves the salts that are built up in rocks, and it dissolves the igneous rock or even other sedimentary rock, and then that gets transported once it's weathered. And the transportation or the movement of that material is called erosion. So in this case, we have two different kinds of weathering. We have mechanical weathering and then chemical weathering, which I just put a box around. In this case, mechanical weathering is where you get ice developing in the fissures and fracturing the rock and popping it out. We often see that in our driveways. We also see it when you put salt in your driveway because you change the freezing temperature of water, but those ice crystals actually can penetrate further into the cement or pavement, depending on what you have, or asphalt. And what happens is, because it penetrates further before it freezes, because it freezes at a lower temperature, you end up getting more sort of that small pockmarked weathering that you see in the spring once you put salt down. But the weathering that's mechanical is a result of mechanical action, like the movement in forces, physical forces moving and popping off sand, gravel, silt, whatever. Then you have the chemical weathering, which is what I talked about just a little bit ago, and that's where you actually dissolve minerals based upon a chemical reaction. They will either be dissolved by water or they will be dissolved by other chemicals that are already dissolved by water, and then they get put into solution and they're moved, transported by the water that just dissolved them. And that's when we talk about sedimentary rock being consolidated of many different kinds of sediment, is because you can have big rock material, how long it's been weathered, you get mud and silt and other things, and it gets into the water column right here and moves downstream. So it's not really you will see different sized material depending on where you are in a stream, but in most cases it's not one molecule or one type of chemistry. So it's usually an aggregate of many different things. And this slide shows us the different kinds of material, or what it looks like once different kind of materials have been weathered. So we have different kinds of obvious action. Could be movement in a stream or ice, depending on the kind of furrows, or if it's round pebbles or chemical weathering or whatever. You end up with, this is obviously a stream bed, If you look on our main page, I show a similar kind of stream bed from Mars and a stream bed from Earth, and they look similar. That's why we think there was water on Mars, because it's the same kind of activity. And then you get this stuff right here, which is breccia, which means broken or broken pieces, and that's basically falling off mountains and forms these talus slopes. We call them talus slopes. You'll learn about that in a little bit. And they're very angular. They don't look to be, there's a little, it looks like a dime right there, but they don't look to be weathered for a long period of time because of the nature of how they erode or are moved off the cliff face. So to reiterate, weathering is the breakdown of the material, the parent material, which would be the rocks, the big hunks of rock, and the erosion is the movement or transportation of that material away from the source. We know that sediment goes through a process of sorting and rounding depending on how it is transported. And obviously the larger stuff or more dense material falls out of the water column first because it takes a certain amount of energy to keep that material in the water column, which means moving or bouncing down the stream bed. In the case on the right, where you get the broken material coming off, let me erase that. You get it coming off the side of a slope or a cliff face, you end up with very angular broken pieces of rock. So basically the type of rounding that occurs or in the type of sorting that occurs depends on the particle size that starts once it's actually weathered out of the parent material, the distance it's transported. So obviously the stuff in the middle is transported for a longer distance because it bounces around, breaks off pieces, or is weathered through the water, as opposed to the stuff on the right where it just breaks off and falls to the base of the mountain, doesn't go, or base of the hill, doesn't go very far. And so it's deposited in a very blocky, angular way, whereas the material in the middle is deposited in a very specific energy way. What that means is in a very specific erosional pattern, because the amount of energy in the water, depending on how far away you are from the headwaters of a stream, will determine the size of the particles that you find. And here are the different particle sizes. I'm not going to really have you memorize them, but just know that gravel is bigger than 2 millimeters, sand is 1/16 to 2 millimeters, silt is 1/256 to 1/16 of a millimeter, and then clay, which is 1/256 of a millimeter, which I find really funny because they're using English measurements. They do this. I don't know why English sort of 1/16 instead of 1/10 or 1/200. I don't know. It's kind of funny that they mix the two type of sizes, and that's because this was done primarily in the English units, so that they just add millimeters. It's interesting. You want to take note of that because when you're looking at rocks, sandstones, or different kind of composites, things like that, you're going to have to look at the size of the material that's in them to determine what they are. And the last thing is the depositional environment in which you find the material is going to be often defined by the physical characteristics of the area. So it'll be like topography, climate, wave action, energy in the water or current strength, I think I have in the notes, and then there's salinity as well, which is the amount of salt in the water. So if it's an ocean environment versus a freshwater environment like we have in the Great Lakes. And these environments will determine what the geological past was for the area. For example, we know that the Michigan Basin has been around for 1 billion years approximately, and that's because of the different layers of sedimentary rock that we find underneath. And when we date them, it goes back about 1 billion years, and it's been a basin, which means we have all of these similar kind of depositional environments, high saline, big layers of salt. This indicates that there's always been a basin or lakes or shallow seas in the area, or deep seas for that matter. I mean, Lake Superior is pretty dang deep. But if they dried up, the lakes, the current freshwater lakes we have a lot of salt in them. Eventually they would leave a huge layer of salt if that water was unable to escape and get into the ocean. And in this slide we can see all the different depositional environments depending on where the parent material sits and then how far it's transported. So it usually starts at the top of a mountain or a higher elevation, and here you have a glacial mountain glacier, which then there's going to be a stream coming out of that. And that stream, which looks like they come down here, it's going to be quickly flowing at the top, so you're going to have bigger material up here, right? The stuff that's greater than 2 millimeters. And then as you get down into the headwaters here, you're going to get the sand, which then is going to go to that 1/16 to the 2 millimeters, etc., until you get the silt at the bottom. Now the stuff here, this is probably going to be sand here, but it's not the end point for deposition here, because obviously you have this other stream coming out and you end up with this delta. So think of the delta coming out in the ocean environment in Louisiana. So the end of the Mississippi, there's big deltas with very fine sediment, fine meaning very small. Then up here to the left, right here where it says alluvial fan, you're going to have probably sand. It's going to be a larger depositional environment at a certain elevation with a specific rate of energy in this water that deposited it, and it's going to have a similar consistency to the lake because it's either a fan from flooding, which is going to have a similar kind of sand in it before it gets deposited in the lake. It might be a little bit bigger gravel for this sort of floodplain that we have right here, but in reality this is all basically a sandy region in here, and that's due to the elevation and the grade, or how steep the slope is, and it's all a similar grade or similar steepness, which in effect makes it the same kind of depositional environment as long as it's being deposited by water. Now with sand dunes, you're moving material around with wind, which means the sand's going to be a finer circumference or radius, I guess, than you would find in the lakes. So we know that you're moving material around, it's getting deposited, but how does it actually become rock? Well, the process by which it becomes rock is called lithification, which means lithify, which is rock, and ation, which means to become rock, lithification, or the process of becoming rock. And so what happens is you get all these layers. Now you can see those layers here. Let me get a pen. All those layers are right here, and you can see they were deposited like this, right? You can see all the layers. And they were deposited in these big flat areas. And this area that you look here, this is the face of some sedimentary rock, and you can actually see these are like broken, eroded edges of a flat plane that were broken off because it's been eroded through, and that's why you see the flat planes like here. But if you can imagine, this plane right here goes off just like this back into the rock. So it's a big flat plane like this that goes back into the rock. Age is the same as all of the other plane at the same, it's at the same plane. Just like in geometry, when you look at it, the plane is the same plane. It doesn't change, so it's the same depositional environment, etc. And you can determine a lot of things based upon that depositional environment. In this area here, you have compaction, right, where you get a bunch of material that's deposited on the top, pushes down, just like pressure that we find in the igneous rock to change the different consistencies of the minerals. In this case, you're getting everything pushing down from the weight of the overburden or overlying sediment, which causes a reduction in the pore space. You're squeezing out the air, and the particles become more densely packed or closer together. In many cases, compaction alone is sufficient to turn this into a rock. For example, I think in the notes I talk about mud becoming shale or something like that. But cementation, which is after compaction or at the same time as compaction, basically glues the sediments together. In this case, it's like an iron oxide in Michigan because the water's so full of iron. It could be an iron hydroxide as well. In some cases, it could be a different kind of salt. For example, sodium chloride will sometimes stick stuff together. It's transient because the water comes along and dissolves it and moves it around some more. We also have calcium phosphate, which is a little less soluble, but still a little more soluble than the iron oxides and the iron hydroxide. We also have the calcium carbonate, which is the carbonate rocks, and then the silicates, which often we really don't know how they cement stuff together because silicate is often sand already, so it's sometimes an action that we don't quite understand, but you get cementation of the rocks and then they stick together, all those little particles. And this slide shows you the process by which we get different compaction and cementation going on. So gravel, here we have gravel that is 2 millimeters in size, which is going to be a little bit bigger than the sand that you have here, which is bigger than the silt, etc. And then the clay, which is very small, fine material. And when we do a lab on looking at the soils, you're going to take your column, your graduated cylinder, it's 100 mils, and you're going to put some soil in it. You're going to shake it up with water, and you're going to let it settle, and you're going to see all these different sizes in the soil, hopefully. depending on where you live. And this is the process by which we're going to identify them as well. So how does sediment become sedimentary rock? Will be determined by the kinds of material which make it up. In this case, you have conglomerates, which can be very big. You can just big old stones that come together and get compacted and stuck together. And then you have sedimentary breccia, which is that angular stuff. Also can get pushed together and stuck together. And those are called clasts, right? Rounded clasts, which are the different pieces that make up the conglomerate rock, and then the angular clasts, which are again the different pieces that make up the sedimentary breccia. And then you got the sandstone, they're all relatively the same. You have quartz sandstone or arkose, which is a feldspar versus, the quartz that we see, the typical quartz. And then of course siltstone, mudstone, claystone. These tend to be a little bit harder to identify and separate, but you can really tell once you get to this size here. You can still see some of the particles in the siltstone. When you get silt and clay, you see how it's a mixture of really fine stuff and some stuff you can see with your eyes. And then of course the clay, which is very, very small. 1/256th of a millimeter is too small for us to see with the naked eye. So the detrital sedimentary rocks, which are these detritus is like stuff left over, are classified on the basis of particle size. So detrital sedimentary particles are classified according to the grain particle sizes we just talked about. You have gravel, sand, silts, and clays. So we have conglomerates, breccias, sandstones, siltstones, mudstones, and shell. Here we have I don't know what the one on the left is in the book, but I think they're trying to show you a conglomerate, which is this area up here, and then this is a breccia, which means broken pieces. So you can see how they're angular. These are going to be rounded. It's hard to see. That's why I think that's what they're showing you. I don't think this is comparable in the sense that they took this picture from this, and if they did, then this is just a picture of the breccia from afar away, but it looks rounded to me. So I think they're actually trying to show you a conglomerate, which is the rounded sort of gravel, and then the breccia, which is gravel with sharp edges, which then moves us on to the chemical and biochemical sedimentary rocks. Now these are the rocks that basically form through cementation of materials or evaporites, where it's a process of evaporation. So you have different textures. You have the limestones and the dolostones, which are pieces of often other shells or fossils or whatever that are stuck together with calcium carbonate. Then you have the dolomite, which is the calcium magnesium carbonates, which these will fizz in the vinegar over time. This dolomite, you have to powder in order to get it to fizz, or what we call effervesce. And then the crystalline, the gypsum stuff, these are evaporites, obviously rock salt. That's one we have in Michigan, and we have it in the Great Salt Lake and all over the place. It's just sodium chloride. All the water evaporates out, and you get the salt crystals, which you'll have in your kit. And you also have the gypsum, which is in your kit as well. We make this into drywall. We make this into road salt and other stuff, obviously, to get rid of, or not get rid of, but reduce the icing that occurs on the road. And then you can actually use rock gypsum on the road. It's just expensive. It's much more expensive than rock salt to break up the ice crystals. Yeah, pretty much any salt will work. Fertilizer will work too. If you're worried about killing your plants that are around your house when you're trying to get rid of the ice, you can use fertilizer instead of rock salt, and that works as well. And then we have the biochemical sedimentary rocks down here. These are just class of shells, which would be the limestone, which is like the carbonate rocks, but it's just all basically shells or fossils. And then you have chert, which is altered microscopic shells of silicon dioxide. We believe that the banded iron formation that we use to make all the cars is actually a chert. Well, I know it's a chert in some areas. Other areas it's so full of iron oxide it looks like you could just melt it down and make steel. Then there's carbon from altered land plants. That's coal. We pretty much know. Lignite, bituminous, and anthracite. Anthracite is a metamorphic type of coal, and then bituminous and lignite are the two coals that we commonly find in Michigan. So in this slide we have a chemical sedimentary rock. The one on the left is called a coquina, which basically just means it's a sedimentary rock made up completely of shells. So in this case, these are all little shells that you see, little pieces of shell, and they're all stuck together, probably a calcium carbonate sticking them together from the shells that get in the water, and then it gets cemented together. And this on the right is probably an oolitic, which is oolitic limestone, which is just um, oids. They're very small spherical grains of calcium carbonate. So that's like pure calcium carbonate. If you were to drop acid on this, they would just fizz and dissolve completely. But that's called oolitic limestone. In your kit, you'll have carbonate rocks, which are, the limestones and the dolostones. Dolostones are interesting because basically the magnesium replaces some of the calcium in limestone, and this occurs in the ocean. And the development of dolostone is not really well understood. But that's the one you have to break down, crush a little piece of it underneath a hammer or with a hammer in order to get it to effervesce if you put acid on it. We also have calcite and dolomite, which are minerals that are calcium carbonate rocks I think you have calcite. I'm pretty sure you have dolomite as well. Calcite is obviously a mineral, and then dolomite as well, but I think you have calcite in your kit, and I'm not remembering if you have dolomite. I'll check. Yeah, I went and checked, and you do have dolomite. It is, let's see, I just saw it, number 26 in your kit. And then we have the evaporites, which are, they're leftovers of minerals, molecules that are left in a basin after the water evaporates. So that's why we call them evaporites. And we have bedded rock salt, which is halite, which means it just forms a plane. And then you have rock gypsum, which is an evaporite of calcium phosphate, which is what we use for drywall. Now, if you look at the calcium phosphate, if you're driving out west ever, you'll notice that there's a whole bunch of what they call bathtub rings, or these lines on the edges of basins where you have white deposits left over from the salts. These salts are actually, quite a lot of them aren't sodium chloride, it's the calcium phosphates or even sodium phosphates left over from water layer that was at that elevation before it dried up. And like I said, we have the bedded chert, which is the banded iron, the red cherts, the jaspers, dark chert is a flint. It's interesting though, because the chert, we really don't know where it comes from. I have chert samples from all over the world. We have chert samples from Colorado. We have chert samples, at least the ones I've collected. I have chert samples from down south. We have some from Kentucky, and we have chert, of course, from the stuff in Michigan. We find it wherever we think there was an old ocean or a shallow sea, I guess is what I should say, and the concentration of iron oxide in the water, or iron, was much higher. It wasn't oxide yet, it was iron. The critters, the microbes that were in the water, utilized it for energy, and they produced a insoluble form of iron, which then fell out. It was actually in their bodies, and as they died and settled to the bottom, they produced these, what we think were layers, or the banded iron layers that we use to make steel. But again, we aren't quite sure if that's actually what went on. And here you see a picture of coal. Now, coal is a biochemical sedimentary rock, and it's composed mainly of plant material. And the plant material in most cases is going to be peat or something like that, which leads us to the next slide, which is basically it's decayed plant material, which then is in low oxygen water. So if swamps are behind my house, like I have a swamp behind my house, and produces this real black clay looking material, which is a peat bog. And over time, that peat gets buried deeper and deeper, and it will heat up. It will become dehydrated, and you get lignite coal, which is very low quality coal. If you burn it, it's very smoky. It has a lot of contaminants in it. What I mean by contaminants is things that don't burn very well. That'll be compacted in the next slide. You see, biochemical bituminous coal, which is much higher in carbon concentration. It's much darker than lignite, and it is indistinguishable from a piece of charcoal in a sense, like if you were to burn it. But it's coal. It's not actually burned. It's just a really high carbon concentration, which makes it look kind of like charcoal. And if this gets heated and compressed, it'll turn into anthracite, which then is a metamorphic coal, and that actually looks like graphite. Anthracite coal is almost pure carbon. Not quite. And to me, it looks like graphite. It looks like pencil lead. So how do we use all of these observations to come up with what was going on in the past? Well, one of them that we can use is something called a sedimentary facie, which means face, and they're used to identify changes in ancient times with the sea level and they determine something called a marine transgression or regression. Regression means to go away, transgression means to come up. So if you look, the transgression, which is the one on the left, you end up with low energy offshore. You get limestone right here produced as you get things piled up. You get shale because there's going to be, this is really fine material, this is less fine material, and then you end up with the sandstone, not sadstone, sandstone, and then the land surface that it builds up on as these seas get deeper or move on to higher up on the face of the mountain or hill or whatever it is you're dealing with. In this case, if you look, if you were to cut through this, you end up with the limestone on the top, and then, so this would be limestone. Whoops, well, that's weird, it disappeared. Limestone. This would be the shale. And then, of course, this on the bottom would be sandstone. Now, if you look at the regression, obviously it's reversed. You have sandstone on the top, and you have shale, and then on the bottom you have the limestone, and then at the very bottom you have the old land surface, which suggests that you started out with a deep marine basin, but it regressed over time. It didn't stick around for a long period of time, and as it regressed, went away rather than came onshore, you end up getting an erosional surface rather than a transgressional surface, and it moves down, and you end up exchanging or changing the position of the layers. And for a transgression, you end up with limestone on the top, which is what we have here. That's kind of a weird symbol. I don't want that. So you end up with the limestone up here, the shale in between, and the sandstone on the bottom, and then the rock, which that ocean or shallow sea was already on. And this would be a marine transgression in the Grand Canyon that is very famous and pretty much is a study of how you identify a transgression in an old marine environment. Another story we can get from looking at sedimentary rocks are sand dunes. And what sand dunes show us is the sand was layered or deposited in an angle to the flat surface or the strata, the area where we would expect the material to be flat. So in this case, a common sedimentary structure that we talk about is something called cross-bedding, which means you get the normal bed that's this going like this, and then you get this other angular sort of cross-bedding associated with that, and it can look a variety of ways. In this case, this is what they're showing you here, is you have the top one where they're coming down at this angle, and then you have a different angle on something that's underneath that, then you have an even different angle under something that's under that, and that you end up getting different kinds of bedding, which suggests that it was deposited by wind rather than water. Sometimes you'll get ripple marks in the bedding, cross-bedding, and that's an indication of water deposition. In this case, when you get cross-bedding as a result of sand dunes, they look like sand dunes basically. They're very easily identified. In the next slide, I show these sedimentary structures, which basically it's the cross-bedding. In this case, we know the direction of the wind because we know it's deposited to the long side. So there are two sides to this. If you look, so I can get my pen, there's a side like this, and then there's the long side like this. So if you were to look at this, you would understand how sand dunes form, which means they pile up and then they run down as they're getting pushed. They do the same thing, get piled and run down like that, piled up. And this produces a structure called cross-bedding, which you see here. They getting blown and then it gets pushed down, blown, pushed down, blown, pushed down. And here it's at a slightly different angle. And one thing we can use, if we understand how these physical features like crossbeds form, they can reveal the climate information for not only the direction of the wind at the time, but also how strong it was, and if it was a desert, or if it was. We also have marine environments, shallow marine deposits, which you get a shallow. In this case, you'd have a shelf which would be like the marine shelf, and then the material comes off and goes like that. It's the same kind of cross bedding. It's a little steeper and flatter than what you get if you in sand dunes. So that's pretty much the sand dune information, because we're going to move now to back to marine environments and how different graded bedding will tell us how these what was there before, millions of years ago. So turbidity, so think of it like gold panning or something like that. If you get a graded bed, that means that there was a lot of turbidity, and the largest particles, or the big ones, settle out at the top of the stream, so the headwaters of the stream, depending on how steep it is, and underneath the fine sediment, because they are going to require more energy to stay in motion, which means they stop being in motion before the smaller particles, and they settle out first. So in this case, you have an avalanche, let's say, off the continental shelf, and you end up getting this cross bedding. No, sorry, not cross bedding, sorry, graded bedding, I apologize, where you get different size particles depending on where they are in the process. So the bigger particles are going to settle out here first, right? And the small particles will settle out further on, but you'll also get bigger particles settling out first here. So you end up with the bigger particles here, and the smaller particles will stay suspended longer, which means they settle out next, and then you get the smaller stuff on top. It's weird how I'm putting it and then it disappears, but anyway. And you can see that right there in that picture on the right, where it's a graded bed that they're showing you. Another story from the past are sedimentary structures of very small ripple marks. Now, ripple marks are very similar to sand dunes, and depending on what they look like, if they are like a sand dune in this case, where you end up with, so here you have the direction of flowing water, and you end up with these scallop marks that are steep on one side and elongated on the other, which suggests that there's a directionality to the movement of the water. And each one of these looks like a mini sand dune. And I actually have seen this when I was in Utah. I went up, I think it was Green Canyon, and I went up to an area where it looked like, actually it was this ripple marks, but I could see an old shallow seabed that was turned up completely sideways, and it looked like I was looking at the bottom of a lake, but it was stone. It's pretty interesting. In this case, we end up with a scallop pattern, but there isn't a gradation to the scallop markings. So here we have the graded bed of the very small directionality type of dunes. I'm putting that in quotes. And here with ripple marks where they exhibit a symmetrical shape and they don't really have a graded appearance to them, like sand dunes. Here we have lagoons and mudflats. Now I have some examples of this from Michigan in the lab, and there's mudstones. They just look like, you pull it out and you can see it has fractures in it, just like this. The ones that we have were filled in by a different sediment, so the cracks were sort of maintained like this, but they erode at different rates. So it's kind of an interesting little rock that we have. But basically, they're mud cracks. And of course, we have the fossils, which show us what kind of land surface was there, if it was dry or marine. And we can use these fossils to determine the age of the rocks because we know the age of the fossils, which then, because we know the age of the fossils, we know the age of the rocks. And we can interpret what kind of depositional environments these rocks occurred in. So here's a question I'm going to leave for you. If you look at modern environments, look at sand textures, look at the cross beds, asymmetrical ripple marks, etc., you might find footprints of land animals, whatever. In this case, this is the Navajo sandstone, and it's a desert dune deposit, but how do we know that? Asking the questions. It's a quite interesting issue because you have all of this cross bedding going all these different angles. Now, is this a desert dune deposit or is this a marine dune deposit? Like, is this due to a continental shelf avalanche? Which obviously you can answer that it's probably not because there's no graded gravel in it. It's all the same size, which suggests that it's moved by wind. And there's no other size gravel in it, which suggests that it is a dune deposit. But then again, um, there are other examples of the type of crossbedding. Directionality of the wind should be all this dunes should be all traveling approximately the same way, which they are. There's a weird one right here, but in most cases they're going to the right, which means the wind was coming this direction and depositing it. And over many long periods of time, this is an erosional surface where you lost the area where it comes up and drops back down. Let me get my pen so you know what I'm talking about. This area, this is the erosional surface right here, comes up like that. So this stuff that's coming down like that originally had a surface like this, which shows that sort of depositional environment, but it's been eroded off so you can't see it. And then of course we have the natural gas, excuse me. And important natural resources of sedimentary rock are anywhere where we have reefs, which are old reefs just like we have in the oceans, which suggests that it was a marine environment, and the oil comes from the deposition of all of these microorganisms and small phytoplankton and other things that settle out over a long period of time and then get compacted, and you end up with oil like we have in Michigan. And so how they identify oil is they'll often drill down, and if they hit a toe, it's called a reef toe, they'll know that they're in an area where you may find oil. Like here we don't have a reef, we have sandstone and some other stuff in there. But really when they're looking for oil, they look for these reefs, these things called reefs, which are depositional things, environments.